In chapter 4, we're going to look a little more closely at alkanes and different types of hydrocarbons. And here we can see that there are different forms of hydrocarbons, is talking about hydrogen and carbon only. And we can have alkanes, alkenes, alkynes, and arenes, and we'll talk about the differences between them. Briefly, though, alkanes just have single bonds between the carbons. Alkenes have double bonds. Alkynes have triple bonds, and then arenes are alternating double bonds, and we'll talk about what makes these aromatic versus aliphatic when we get to that point in arenes. The general structure for a linear alkane, which means it's just a straight chain, is CnH2n plus 2. So if we're looking at methane, for where C is 1, the 2 times 1 is 2, plus 2 is 4, so you can see that we have 4 hydrogens. So if we make this a 2-carbon chain, then we're going to use this same equation to determine the number of hydrogens, for example. Because they have single bonds around the carbons, all of the carbons and their attachments are 109.5 degrees, and they're tetrahedral in shape. So we're going to often look at these as kind of these zigzaggy lines. You can see here zigzag because of that tetrahedral shape, and this is why we actually write these out as line structures in a zigzag, because that's more actually showing us what their three-dimensional shape is. So here we have butane, and we can see we have these 4 carbon groups here, and we are going to talk about constitutional isomers being still 4 carbons, but we might be able to arrange them. We basically have to break bonds and move the carbons around to make this 2-methylpropane, for example. So we still have the same number of carbons, the same number of hydrogens, but bonds have moved, and that is what we call a constitutional isomer. So you should know that term and what a constitutional isomer means. Here are some other examples. 5 carbons, pentane, we can have 2-methylbutane, 2,2-dimethylpropane. So you'll notice that 1, 2, 3, 4, 5, we still have the same number of carbons, the same number of hydrogens if you add them up, but these are constitutional isomers. That's compared to conformational isomers, where we still have a long chain, for example, but then that chain orientation is just different. So you can think of this as a different twist of the chain. It's a conformational twist, but it's not a constitutional change. To change the constitution, you have to break bonds and then reform. You still have the same amount. You'd have the same types of atoms and the same number, but they're organized in a different orientation. We're going to start talking about naming or nomenclature, and this is the kind of system that is used to name different hydrocarbons. When we're talking about single straight chain alkanes, they have a different name depending on the number of carbons that are associated with them. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, and so forth. So these are the basic names for those straight chain compounds, and I want you to know up to 10. So I do want you to know up to decane. When these are different groups that are off of longer chains, we actually shorten these full names. So meth is the base. So sometimes you'll hear a methyl group, ethyl group, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, decyl. So if that is given a YL ending, that just means that this is a substituent group or a group off of a different chain or a different compound. Here are some non-straight chain alkanes, and this is cyclopropane, cyclobutane, cyclopentane, cyclohexane. You'll notice that we still go by that same naming system, except for it has a cyclo in the front to indicate that it's circularized. We do lose the equation changes. We do lose 2 hydrogens when they're a cyclic compound, so that does change these groups a little bit, and they are no longer constitutional isomers anymore because we don't have the same number of carbons and hydrogens. So cyclopropane is not a constitutional isomer of propane because the number of hydrogens differs. We are going to go into this systematic naming process. Although sometimes compounds will have different trade names or generic names, systematic names give you a little bit more information about the functional groups and how they're organized. So for example, propionic acid, the oic acid, is indicative that this has a functional group that's a carboxylic acid. That's actually methyl ethyl propyl. So it's 3 carbons long. And that's what that propionic acid at the end of this longer phrase is telling us. Here's a phenyl group that we see here. And then we have the methyl propyl group. That's a methyl propyl group here. So we'll talk about how we determine those things and how we name them. We're not going to start at something this complicated. We're going to start a lot easier with just some of the smaller chains of carbon. So these names that we are given are going to have typically a prefix. What are substituents? So any groups that are off of this main chain. The parent group, and that's going to be the longest carbon chain, and then a suffix if it has a functional group that's going to come at the end. So an example of the longest chain, this is the parent group. The starting point for this is to identify the longest carbon chain, and that is given by these names again that I introduced you just a few moments ago. You always want to find the longest chain, and it doesn't matter the orientation that that chain is in. So regardless of it's straight like this correct one or incorrect one, if this incorrect one had a few more carbons off of it, it could go this way. So it's just based on the longest length that you can find. So you have to look at all possibilities. So if I come straight here, I get 8 carbons. If I bend that down, it's 7. So this is the longest chain that we're going to use in order to identify the base, that parent group. So this would be an octane. And we'll talk about these are substituent groups. Those are groups coming off of the longest chain. So we'll talk about those next here. And if we have 2 chains of the same length, then which one do we use? So we're going to use, here's another rule that we actually use, if we have more substituent groups, that's the correct chain to choose. So you can see this example, we could do 7 atoms as the longest chain, so a heptane, and we can have 2 substituent groups or 1 substituent group. We're going to use the naming convention that uses 2 substituent groups. This is going to actually be easier in the long run when we have more substituent groups. The next rule is that we want our numbers. We actually number each of the carbons in our parent chain, and then those numbers are going to indicate where our substituent groups come off of. And we want that number to be as low as possible. You can see here in the example, we have the correct numbering from left to right and the incorrect numbering from right to left. And it's not incorrect because it's numbered from right to left, but because we don't hit that first substituent group until the number 3, versus if we number it from left to right, we hit it at number 2. So we want the lowest numbers possible. Here we'd have 3, 4, and 7 versus 2, 5, and 6. That first number is important to have that number lower. So the first substituent group we hit, that's where we want to number it from. Here's another example where if you number it from left to right, you hit that first number still at a 2, but the later numbers are higher if you go from right to left. So here we see the example, it's 2, 3, 5, versus this way that it was numbered, it would be 2, 4, 5. So 3, 4, 5, those 3 and 5 are smaller numbers than 4 and 5, for example. Another rule that we'll get practice working on, and it's not the end of the world if you get some of these wrong at first, but typically you want these to be alphabetically organized. So if you have 2 different ways and it's hitting this, see, we'll hit this ethyl first at 3. If we number it this way versus this way, we hit the methyl group first. E is alphabetically before M, and typically we would use the alphabetical organization of that to have that be the lower number. So earlier number should be the lower letter, or the earlier letter should be the lower number. We will also be using each different substituent group should have a different number. And you can see here it would be 2, 5, and 6. If you have multiple substituent groups coming off of one carbon, you might have, or similar types of compounds, you would number these 2,6 dimethyl groups. So if you have 2 or 3 or 4, you would use this different way to indicate 2, 3, or 4 groups and so forth off of those different chains. Here's an example of that system. We have 2,6 dimethyl because we have a methyl group at the 2 and a methyl group at the 6 carbon. And you'll notice this is the full name. It would be 5-ethyl. E becomes before the methyl part. We're not taking it in front of the D part. So it would actually be 5-ethyl comes first, dash 2,6-dimethyl. We have the 2 and the 6 methyl groups. And the parent chain is an octane because it's 8 carbons long. It's an ANE ending because it's just all single bonds. There are no double bonds in here. Just something important to point out. Between numbers, we always have commas. And between numbers and letters, we always have dashes. So 2,6 dash name. You'll notice that throughout this system, we'll notice that if you are between numbers and letters, there's a dash, even if the letters first and then the number. So that's always consistent. And then if we have numbers, there are always commas between them. So that, and the other thing that we'll also notice down here is all of these names are kind of pushed together. So this dimethyl octane is one word at the back end of this naming structure. So dimethyl octane, one word when we're doing this. I like to walk through a few examples for naming these different alkanes. On this first one on the top left, we need to actually number this from the right to the left. We get a 1, 2, 3, 4, 5. So that is pentane. So you can see that pentane is the parent group. Off the second carbon, we have a methyl group, just 1 carbon. And off of the third carbon, we have another methyl group, just 1 carbon. So it's a di. We have to add that di in there to tell us there are 2 of them. Dimethyl pentane. On the next one to the right, we need to actually number it from the left to right this time. 1, 2, 3, 4, 5, 6, 7, 8. If I had numbered it from right to left, it would be 1, 2, 3, 4. So we would hit this methyl group at the same point. But remember, the E comes alphabetically. So this is a methyl group and an ethyl group. There are 2 carbons here. So that ethyl group is alphabetically first. So we have that 4 ethyl, 5 methyl, and it's 8 long. So the parent chain is an octane. The group down on the lower left, we would start from the right side. 1, 2, 3, 4, 5, 6, 7, 8. So we again have that octane is the long chain. We have the 3 methyl. And we also have a 4 methyl. So we have to add those together to get that dimethyl. And alphabetically, this ethyl group on the 4 carbon comes first. So 4-ethyl, 3,4 dimethyl octane is the name for that one. And for the lower right, it looks a little bit tricky because we have a movement of where these are. We might think that this would be the longest chain, but here we get the chain with the most number of constituents. It would go this way rather than just straight across. So it's a little bit trickier to visualize that. And we would start on the numbering on the right side. So 1, 2, 3, 4, 5, 6, 7. And we have a 2, 3, 5. So 2, 3, and 5 trimethyl. And M comes before P, and that's your 1, 2, 3. That's methyl ethyl propyl. So a propyl group on the 4 carbon as a constituent group. And 7 is the long chain number, so that's heptane. So 2, 3, 5 trimethyl, 4 propyl heptane is the name for that compound. I do want to point out that there are a few different special substituent groups that are commonly referred to. And here is a difference between a propyl group. A propyl group is the one we just mentioned on the last slide. And you'll have your parent chain, and then you'll have a methyl ethyl propyl group. So that's 3 carbons. And that is typically how, if it's coming off of the end and that chain extends off of it. However, right, that's the difference between coming on the end. If we're going to attach from the middle of that group, methyl ethyl propyl group, then it's going to be called isopropyl. So it depends on the attachment point. If the parent group attaches to that middle carbon, it's isopropyl. If it's on one of the end carbon, then it's just a propyl group. Butane, there are also special circumstances for butane, and if we're looking at the attachment on the end, that's where we would just have the normal butyl group. However, if we're attaching that where they're going to be attached, the original attachment point, right, comes in the middle, then it's going to be a sec butyl, and it wouldn't matter if it's parent and the attachment point was like this. It's still the same compound, it's just rotated around. So these would be both sec butyl. And you can also see that we could change this. We could take one of these carbons off and we could attach it to a different point. And you might have, here we have the methyl ethyl propyl butyl. It's coming off of a different chain point, and that's when we get the isobutyl containing the isobutyl compound. And then the tert butyl is, we still have 1, 2, 3, 4, but the parent is attached to a carbon that's attached to 3 other things. So we have butyl, sec butyl, isobutyl, and tert butyl. So just so you're aware, if you see those names, that you are able to distinguish what those actually mean, and you're not thrown off by this in the book, for example. So just an example of one of these special cases, here is one that's given to you in the book. We look for the long chain, and we could go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is the long chain. And then we are going to number it based on when we hit the first substituent group. So it looks like from right to left, we hit 1, 2, 3. We hit that in the 3rd position. And then we have to identify the substituent groups here. We have a methyl group on the right side. And then we have methyl ethyl propyl butyl, but you'll notice it's a special different type of butyl. It's going to be that tert butyl. So we would name this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that means that's a nonane, is our base group. And we have a 3 methyl group and a 5 tert butyl group. So I mentioned most of the time we don't have dashes between the names. This is one of the instances where we have the iso or tert. Those are special circumstances where we put a dash between the tert butyl or isobutyl to distinguish those different types of butyl substituent groups. Here's another thing that I'll ask you to do is actually take an IUPAC name and make it into a chemical structure. So always the starting point is identifying the parent group. So here we're always going to look at the end and identify that parent group. So here we can see a decane group. And we'll start with a 10-chain carbon chain. And then we'll just draw it out in this zigzaggy structure that you can see here. We'll just count. I usually start by starting with the number 1, and I'll make a little circle here just to give me a starting point. And then I'll go to 1, 2. So I'll start with the 1. So for me, what I'll do is I'll start with the 1. I'll kind of draw a little circle to start 1. And then I'll go to 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then that will be my end group. So then I'll have this part completed, and then I'm going to count a number typically from left to right just because it's easier to just have a convention. And I know that I'm going to go to the 6 group. I know that I'm going to have at the 6 carbon an isopropyl group, so you can see that can be drawn out here. I have 3,3,7 trimethyl groups, so I have 3 methyl groups. I have 2 of those on that 3 and then 1 on the 7. So that's how I can draw that out. And this would be my final answer, which you can see down here as well. So it's easier to actually, I think, to look at a name and draw it out. Naming the drawing, I think, is a little more challenging because you have to put all of those pieces together. So the next step is to practice some of these. You'll have a worksheet with both the structures, and you're going to name these, and then you have some names and you have to draw out the structure. So now's a good time to practice those. Go back on the slides that I just presented. All of the answers and information on how to solve these types of problems should be there. If you're not quite sure, maybe review those and then come back to working out those names. Our next steps to start to name some of the cycloalkanes. So first of all, when you have a cyclic compound, that's going to be your starting point for identifying and naming the compound. So if there's a cyclic compound in there, that's going to be your parent. And here we can see that there is a 6 carbon ring, and it would be a hexane if it were linear, but because it is cyclic, we add that cyclo on it. So cyclohexane is our base compound. Next, we want to identify the different substituents on it. So we don't need to number it if it only has a single substituent. So down here, for example, we would just add the methyl for the substituent group, or the tert-butyl if that is the substituent group, if there's just one. Now, if we have 2 of them, now we have to have some different rules for naming these. And here we are going to, again, give the lowest number to the alphabetically first compound. So we have a methyl ethyl group, or we have a methyl group. And since ethyl is alphabetically first, we'll number it and give it the lowest possible number. So we'll give it 1, 2, and 3. We won't go this way around the ring because that will give us a bigger number for the methyl group. So here we have 1 ethyl, 3 methyl cyclohexane. So that's how you would name cyclic compounds. Sometimes common names are used. For example, if you have some of these interesting types of cyclic structures where they're attached, and we have basically 8 different carbons here, this is referred to as cubane, houseane, churchane, basketane, just kind of funny names for these. Dodecahedron and fullerene, you may have heard of Buckminster fullerene. These are different types of interesting compounds that have some interesting possibilities for uses in various types of nanotechnologies. You might also see something like isopentane, where we have methyl ethyl propyl butyl. It's a butyl group, but because the added carbon here would make it a pentane, sometimes you'll get common names like that being used rather than the IUPAC name, the standardized name, which would be 2-methylbutane. So you may see this sometimes on different chemical bottles or in recipes. This goes back to some common names that were perhaps used before we really knew what the structure was. In the lab, we really look at some of the physical properties, and in the previous chapter, we talked about intermolecular forces. Remember, all of these carbons, as we get longer and longer and longer and longer, we are only going to be dealing with van der Waals forces. But the bigger those carbon chains are, the more interactions they'll be able to have with each other, and the more that those van der Waals forces add up and allow these chemicals to be sticky to each other. So really small molecules like methane, ethane, propane, those are going to be our bottled gases, for example, that we might use in cooking or heating our houses. And these are going to be typically have a boiling point below 20 degrees Celsius. Once we get into octane, you might hear of that referred to in your gasoline, then we start to increase that boiling point to 20 to 200 degrees Celsius. Kerosene, different oils, lamps, fuel oil that you might use. We talk about jet fuel, diesel fuel, lubricating oils, tar and residue that we use in asphalt. Then these boiling points get to be a lot heavier and a lot bigger. And as those chains grow and those van der Waals forces are increasing between those different molecules. Just because it's interesting to look at, if you have just crude oil, you typically will distill that or change that into gasoline. It's going to be a little less than half of that. We get some diesel oil out of that, or diesel gases and heating oils out of that. Jet fuel is a small component. Lubrication, waxes, and different solvents, different oils. And then you can see that petroleum and different chemical synthesis reagents and plastics are made out of just a little bit of that. So you can see here all of the uses for that crude oil breakdown and where it's coming from and why we want to break those down. And that's the way that we get that is through this distillation process and separating those out so we can have different uses for those different components and different lengths of carbon. This is again just telling you what I mentioned before. The different lengths will dictate the boiling point. So methyl ethyl propyl butyl versus methyl ethyl propyl butyl pentyl hexyl. So butyl versus hexane, butane versus hexane. We're talking about a boiling point of about 0 degrees versus almost 70 degrees Celsius. So that's a big change by just adding a few carbons. And then we add hydroxide group, which has the capacity to hydrogen bond. Then it increases it quite dramatically. So you can see that boiling point increasing and the melting point as well increases with those different capacities. So again, increasing strength of the intermolecular forces by having more carbons or different capacities based on their the makeup, that changes the boiling and melting points. Depending on how the organization, it will also potentially change the melting and boiling points. You can see this really highly branched compound, which has a lot of different carbons off of one central carbon versus a more linear one that might be able to kind of lay on top of each other more. You can see that boiling point difference, 20 degrees Celsius, and that's due to the surface area and the ability for these compounds to lay on top of each other over on the right side, but on the left, it would be harder to interact and have those interactions, those intermolecular interactions. Based on what I just spoke about, I'd like you to arrange the following compounds in order of increasing boiling points. So start with the lowest boiling point here, and then just go up and up and up till you get the thing that would have the highest boiling point based on its structure, size, mass, all of whatever you feel like is appropriate. If you're not sure, go back and watch the last few slides. One of the important components to recognize about alkanes is that there is and can be rotation between these bonds. So this isn't something that keeps this interaction or this bond from rotating. So here we have a red hydrogen just to show you that this can rotate and move. And these are called conformational isomers. Again, I mentioned this at the beginning of this lecture, but these are conformations, two different conformations of the same type of molecule. There are different conformational descriptors. So this is the eclipse. So you can think of about a solar or lunar eclipse where they are over each other. And that's where these are in the same orientation. If I rotate, for example, that front one, 60 degrees, this is referred to as a staggered conformation because we have in the back, this is pointing up. In the front, it's pointing down. So staggered versus eclipse. We're going to talk about what that means and what that does and what orientation is the best in terms of energy and where mostly these molecules are oriented and organized. This is just another view of that same thing where you can see that eclipsed form. These things are really right over each other. And all of these different atoms, these hydrogens on the outside, are in the same orientation, and that staggered conformation, everything is 60 degrees apart from each other. This is how we would do this in terms of being able to draw this out and describe it and explain it on a piece of paper. This conformation, what we're writing here, this carbon is really the front carbon, this little dot right here, and this big circle is the carbon behind it. And then that allows us to draw the lines to the attachment points here. So this next step, if we draw this 3 lines, that represents the 3 hydrogens coming off at those different angles. And on the back carbon, they're coming off in the staggered conformation here. So you can see these lines touch the back on the outside, and that front carbon, they're coming right to the middle point. So this is equivalent how you would draw these out, basically transform this 3-dimensional image into something that you could draw out. So this is something I'll ask you to do right now. I'd like you to try to redraw that out. So here's a ethane in the staggered conformation and an ethane in the eclipse conformation. I'm going to try to draw that out for me, and pause here and see. I'm going to show you the answer in a moment, but try it out first before you look at the answer. See if you could recreate that image and then transform it into the eclipsed formation. So this is what these would look like, and you can see this was already drawn on that last slide, so it should be pretty easy to recreate. This is what the eclipse conformation looks like, and you would again come off that back carbon and show that these are in the eclipsed or overlapping conformation. You can look at this for something longer than just 2 carbon chains, but you're only going to consider 1 carbon-to-carbon interaction and bond at a given time. So here in the blue, we're going to say that's in the back side, and this red one's on the front side, and this is how you would draw it out. So these are all going to be the red hydrogens over here, and then this is the back version with the blue substituent groups on that back end. So this would be the staggered conformation of that, and this would be the version of the eclipse conformation. So again, you're just looking at this front and the back one. You're only looking at 2 carbon bonds at any given time. There is actually a reason why I'm telling you this. The reason is, depending on what these side groups are, if they're hydrogens, it's not as big of a deal. But once we start putting bigger groups here, bigger substituent groups that are substituting for these hydrogens, all of a sudden there are going to be big impacts in terms of the energy considerations and if these are going to attach or not. So these conversations we're having right now about this staggered or eclipsed form, there's a reason for it, and we're going to talk a lot more about it later. But this is really on a smaller scale level. These small changes in the orientation still have energy considerations. So whenever we're talking about energy considerations, if you can be in 2 different energy states, the lower energy state is typically the most stable and the most occupied. So these tend to form in the staggered conformation. They'll tend to be in the staggered conformation if we're talking about statistically, for example, the lower energy is more likely to be in this state than it is in the higher energy state, because there is less likely to have that energy to be in that state. So you can see that eclipse form, that's when these are right on top of each other. They're at the high energy state versus the staggered, where these are alternating and they're not overlapping each other. You can just kind of think about that as these electrons in these different clouds and these different hydrogen atoms, they don't necessarily want to be that close to each other. So they're trying to socially distance themselves and separate themselves out as much as possible. And this is the format and the version and the lower energy state that they prefer to be in. So I'm mentioning being in that eclipse format has more energy, takes more energy. If they're just hydrogen, it just adds about 4 kilojoules per mole of these molecules. If I add a methyl group as a substituent, it gets to 6, so it increases it from 4 to 6. And then if I add 2 methyl groups, it goes from 6 to 11, so it almost doubles at that point. So having bigger groups here changes the amount of energy required to be in this orientation. And we can look at this and rotate these all the way around. So if we have this compound here where we have these two methyl groups coming off, we can see that the highest energy level is when both of those methyl groups are in the eclipsed form, and the lowest energy levels are on the outsides here, where those two are on the opposite sides of the atom in the staggered form. So eclipsed is highest when they're right on top of each other, staggered were the exact opposite sides of either of their respective carbons. And then there are intermediates where they're still close to each other, they're not on the other side, but they're also staggered and or overlapping hydrogen carbon groups. So just some examples of where this is going to be leading to. And then we'll also start looking at what's going to happen when we maybe have things that can't freely rotate, for example, when we have double bonds. So these are all things that we're going to come back to. And this is something that you should be able to understand, recognize, and kind of think about in terms of being able to recreate it or understanding these energy levels. Okay, so for the end of this lecture set, there are a couple of things that I'd like you to try. I'd like you to convert these into Newman projections and indicate that, show that Newman projection around these indicated bonds here and recreate that image. So write that down and bring that to class. And then I'd also like you to follow this, which is the following are possible Newman projections for 2-methylpentane. So I'd like you to first draw out 2-methylpentane. Now that we've named those and we've shown you how to do the IUPAC naming for that, you should be able to draw that out. And then I want you to determine, looking at these Newman projections, which ones of these three are possible to make from 2-methylpentane. And finally, I want you to rank these A, B, C, and D in order of increasing energy. So lowest energy, you can rank it a number 1, highest energy with number 4. So do that as well and bring your answers to class when we meet to check to see if you did this correctly. And then that's all we'll cover for right now for the different types of alkanes and some of the energetics involved. And we'll start talking about some of the different orientations and organizations of some of the cyclic compounds and some other factors for alkanes.